right. I need my card ready. Hold on. This, my friends, AP Physics 1, Momentum, TIPERS, Assignment 2, and we'll try to get through all of them. We'll see. We might have to split them in half. Alright. I may have to redo some of my drawings here. The object goes from moving 3 meters per second in the positive x direction to 7 meters per second in the positive y direction in 5 seconds. So the impulse given to it is 8 kilogram meters per second. I'm not sure where they're getting the 8 from. Since the impulse equals the change in momentum, okay. Alright. So I'm alright with this statement. If the 5 seconds doesn't come up if we can just get the change in momentum. But I'm not sure where they get the 8 from here, ladies and gentlemen. So here's the way I look at it. You had momentum this way, to the right. Well, the first, and you ended up this way. So the first thing you had to do is get rid of that right-hand momentum. So that would have been a left-hand impulse, a left-hand change. Something that would counteract and get rid of it. Then you had to speed it up the other way. So your change is this. It's a vector. Remember, momentum is a vector. So this is 14, because the mass is 2 and the speed was 7. This is 3. Not worried about times 2, which is 6. So this is actually 6. 3 meters per second times 2 kilograms. So I got 14.6. Get my calculator out. I'm going to do some Pythagorean-ishness. I don't think I did that right here. Yeah, I did. I guess that's right. So, anyway. I got 14 squared plus 36, which is 6 squared. And then I get the square root of that. I get 15.23. So I got change in momentum of 15.23 kilogram meters per second, directed up and to the left. Up because I have to make it start speeding up this way, and to the left I got to get rid of this guy who had momentum to the right. Yeah, not bad. I give angles and stuff, but I think if you wanted to give this angle, you could. The change in momentum, that's fine, but this is fine. Alright. Force versus time graph. First time we've seen these, very important. You can imagine, graphs are almost always important. Force versus time graph. Area under. Area under is impulse, change in momentum. So right now, commit that to memory, and I never ever want to have to say that to you and have you be like, oh, I didn't know that. After you watch this video, this is one of those things you're going to know. Force versus time. Area under the curve is impulse, change in momentum. You can remember, look at this interchangeable words. I won't even say This is not to be confused with, but definitely should be kept in comparison with force versus distance or displacement. Remember, the area under that graph is work. I don't know what the word, that's not area, but you get the idea. Area under is work. So they're both important, but you have to recognize the differences here. If it's force versus time, we're in the world of momentum and impulse. If we're over here in force and distance, we're in the area of work and changing kinetic energy. Okay. We're not in that world right now. So basically, they break it up into 0 to 2, and then 2 to 4, 4 to 6, and then 6 to 8, and then 8 to 10. Okay, so I didn't even put E in here. My apologies, but E's got to be the lowest of 0. I didn't even realize I wanted that. So the biggest area here, well, this one has 2 seconds and the full 3 up. That's got to be the biggest area. This would almost be there because it's missing this. So I'm going to go, E number 1, E's 2. That looks like a bigger triangle. That's 3, 4, and then obviously this is 5. So 2 to 4 seconds would be B. then C, and then A, and then D, and then E, yes, would be not there. So, but it's just the area under. That's what you want to know. Change of momentum is the area under. So if you knew the initial momentum and you figured out this area, you could find the final momentum, right? If you know how much you started with and then what it changed by, you could then find out the new momentum. Keep that in mind. Student calculates that the impulse applied to the, let's say, a 10 kilogram box initially at rest moves along a frictionless horizontal surface. The horizontal force to the right is applied to the box. The magnitude of the force changes as a function of time. Okay. Student calculates that the impulse applied by the force during the first 2 seconds is 4. Whoa. And that the impulse applied during the following 3 seconds is 6. Let's go back to this. I think Homie, I don't know what the student's name is, but I think our friend has a little bit of a problem. And here's why. It would be 4 if you just took the area of this whole triangle, this whole square. But this is a triangle, and they taught us way back when that triangles are base 1/2 base times height. So your base and your height are both 2, that's fine, but don't forget your half. The impulse here is just 2 Newton seconds. That's another way of writing kilogram meters per second. Now, for the rest of it, he says the rest of it is 6. So I got this section here, which is going to be 1, 2, 3 seconds times 2 high, so that's 6 Newton seconds. But then there's this section, which is 1, 2, 3 times 2. So that's going to be cut in half because it's a triangle. It's 3 Newton seconds. So I have a total impulse for this entire thing of 6, 7, 8, 9, 10, 11, of 11. So yeah, you just seem to have some trouble with geometry, it looks like. All right. Two skaters, a large girl and a small boy, are initially standing face to face, but when they push off each other, if you're not picturing me and Ms. Busby, you're missing out, really. I mean, really. It's just... All right. No, I still outweigh her, I'm sure, but she's taller than me. All right. After the two skaters, but they push off each other. Now, we all know that if it's me and Busby, we know what's happening there. Who's doing the pushing? Busby's smacking me right in my face. After they are no longer touching, the boy has more kinetic energy than the girl. A physics student who is watching makes the following contention about the forces that the boy and the girl exert on each other. Since the boy has more kinetic energy, he also has more momentum. So the girl had to have pushed harder on him than he pushed on her. I know it's a fictitious student, but I still was driven to do that. They can't call this person a physics student. They're a novice at best. They are not a student. Because there's a violation of Newton's third law. That's impossible, right? Every action, equal and opposite reaction. Doesn't really matter who pushed who. If Busby pushed me, I pushed her right back without even trying. Every force comes in pairs. All forces come in pairs. And they're equal and opposite. So the forces, the reason for me having more kinetic energy have nothing to do with the forces. The forces on us are the same. And they're for the same amount of time, right? She can't touch me longer than I'm touching her. If she's, right? Like if there's contact, you know. So we experience the same force for the same time. Our impulses, our change in momentums are the same. We have identical momenta after she pushes me off. But that doesn't mean we have to have initial kinetic energies. Why? We looked at this earlier. Because velocity gets squared in kinetic energy. And I will have more velocity. Why? Because the same force on me is going to speed me up faster. And so, assuming that I have less mass. So that means that we may each have 120 units of momentum, Mine would be, say, 10 mass and 12 speed. Not worrying about positive or negatives. But the larger person's might be 12 mass, right? And 10 speed. We have the same momentum, but if you calculate our kinetic energies, I'll have more because this gets squared. Two boxes on a frictionless surface, momentum and speed. Two boxes tied together by a string. This is a string. And are sitting at rest on a frictionless surface. Between the two boxes is a massless, compressed spring. The string tying the two boxes together is cut, and the spring expands. Strings and springs is like a Dr. Seuss book. Pushing the boxes apart. So just like the previous problem with two people pushing each other, whatever. The box on the left has 4 times the mass of the box on the right. Okay. After the string is cut and the boxes lose contact with the spring, will the magnitude of the momentum of the box on the left, will the momentum of this one be more, less, or the same than this one? Here's how we reason through this. This force has to be the same on both of them. So they experience identical forces for identical amounts of time, because once it loses contact with one, it's going to instantly lose with the other. So they experience identical impulses. They started with 0 momentum. Their impulses, their change is the same, so they have to end with the same. So that's why I went with the same. At the instant after the string is cut that the boxes lose contact with the spring, will the speed of the box on the left be greater? Okay, so same force, but it's not going to speed up. This box is not, under that same force, is not going to speed up all that much. Well, not as much. In fact, it's going to have 1/4 of the speed, I believe, as pardon me while I try to focus this. So this should be going slower. So let's make sure we get this right. Will the speed of the box on the left be going greater than? No, less than. Should be less than. It still has the same momentum because even though it has less speed, its more mass accounts for that, and it ends up having the same momentum. All right, now let's just skip that one. We're going to go into this. Perfectly good pencil I destroyed. All right, first one, looking into collisions. So these two, we look at them together as a system. So what would their momentum be prior to this collision? Well, the momentum of this car here would be we'll just use the units that are present. 2 times 5, that's 10 with 3 zeros, right? So that's 10, 1, 2, 3, it's 10,000. And I'll call officially anything going to the right is positive. That means this one is 4 times, so it's going to be, I don't want to mess this up, but I'm pretty sure it's also 10,000. You want to go 400 times 25, 10,000. So this one has negative 10,000. So what is their, and the negative makes a difference here, it's a vector, so what's their total momentum before the collision? You're right, 0. It's just a weird way to have 0. So after the collision, conservation of momentum says, if all the forces are internal, after the collision, whatever momentum you had before, you have after. So after the collision, it's going to have 0 momentum, which means, in this case, 0 velocity, because they're stuck together. And the only way one object can have 0 momentum is if it's not moving. So if you go through them, all of them have identical momenta coming in and coming out, at least the magnitudes, one positive, one negative. So all of them before the collision have a momentum of 0, and they all stick together. Now, if they bounced off, it's different. The speeds of the individual cards could, it's going to possibly vary, but in this case, it's going to be all 0. All right. So here's a classic momentum question. You can look at it a lot of different ways. You could be sitting in my classroom and someone's standing on a tall ladder. It doesn't have to be bullets. They can drop a lump of clay, soft clay, on top of your head. or they could drop a rubber ball that has the same mass on your head. Well, this would be like the lump of clay. It would come in and it would stick. And it requires certain force. So in this case, it would transfer momentum to this block. In the case of the rubber bullet here, it's like the rubber ball. It's going to hit and bounce back. So does this or this experience a bigger change in momentum? We've seen things like this earlier on. And then you got to be careful. We can make up numbers if you like. This initially has a momentum of, we'll make it, it's kind of a ridiculous thing, but we'll do 1 kilogram. That's a way big bullet, but that doesn't matter. Times 10 meters per second. It's a ridiculous thing, but that's all right. Doesn't matter because it's just numbers anyway. So this is positive 10. What is it here? 0. So what's our change in momentum? It's our final minus our initial. So it's 0 minus 10. So it's negative 10. All right. What about this one? We'll say it's also 1 kilogram. It's also moving at positive 10. But when it bounces off, it's moving at negative 10 meters per second. So its final is negative 10 kilogram meters per second. It's minus its initial, which was positive 10. And this is a change of negative 20. It's a larger change. So this thing, in bouncing will always produce a larger change in momentum because one direction's positive and the other's negative. So you're going from positive 10 to negative 10. That's 20 steps. Not 0. Positive 10 to 0, that's 10 steps down. But then here you have to stop and then keep on going to speed up in the other direction. So it's 20 negative steps. So the speed of the wooden block after the collision is going to be greater in this case because the change in momentum for this is larger, and so the change in momentum for this is going to be larger. In case B, well, the speed of the bullet, all right, now, I guess I kind of messed this up a little bit. I shouldn't go around making that the same speed coming off. Why? Well, you tell me why, if you think about it. So my mistake here leads right to this question. Will the speed of the bullet after the collision be greater than, less than, or the same as the speed just before? If it bounced off, this is more of an energy question. If it bounced off and had the same speed like I drew, just to be quick about it, and to show how this worked in the negatives, that means it kept all of its kinetic energy, didn't it? And the system only had its kinetic energy. So there's no way, if it bounced off at the same speed, this can't move. There's no energy for it. But it is going to move. So that means some of the kinetic energy of the bullet had to go to the kinetic energy of the block. So the bullet should be coming out slower. The speed of the bullet after the collision will be less than when it came in. Has to be. If the block is moving, has to be. So this part right here is actually misleading. Maybe I should have made it negative 9 kilogram meters per second. And that would have given the block 1 unit of momentum. All right. Last one. 2 identical carts traveling opposite directions, carrying different loads. All right. These carts will both be at rest after the collision, since the initial momentum of the system is 0 and the final momentum has to be 0 also. Well, let's find out those momentums real quick. This guy will say has a negative momentum of negative 160. Once again, I'm not worried about the units. So these centimeters per second, we would never really, but as a measure, it's fine right now. This is 160 positive. All right, so true in fact that the total momentum of the system is 0. And so by conservation of momentum, it has to be 0 if all the forces are internal, which they are. So if you have one object when they link together, the only way to have a 0 momentum is to have a 0 velocity. So I'm on board with Alex right off the bat. We could look at these. If it were true that it would mean that they would have 0 kinetic energy after the collision. Well, yeah, that's true. No, it wouldn't violate the conservation of energy. There'd just be a lot of heat and stuff lost in here. So one of the things you should have picked up by now is if a collision is perfectly elastic. In other words, the things bounce each off each other, like these, like the rubber bullet off the wooden block. If it's completely elastic, then kinetic energy is conserved. So the kinetic energy before has to equal the kinetic energy after. So initial and final. But if it's inelastic, things stick together, even in some small way, but in this case completely, then kinetic energy is not conserved in inelastic collisions. And that is something that this person, Belinda here, didn't pick up on in class. I think after the collision, the pair of carts will be traveling left at 20 meters per second. That way the conservation of momentum and conservation of energy are both satisfied. That person is just looking at the role of velocity, aren't they? They see this as being 20 more than that. It's not true. They're identical momenta. All right.